It's impossible to discuss the concept of a black hole without first delving into the details about light, or electromagnetic radiation. In the absence of light, we get darkness, or blackness, which is how black gets into the name black hole. Black holes do not allow light to escape from their interior, so they appear completely dark. Our intuition regarding the properties of light can sometimes be misguided. So let's discuss some of light's fundamental properties. When a beam of white light is passed through a prism, the white light that enters is separated into a rainbow of colours, spreading out to the other side of the prism. Each of the colours in the rainbow corresponds to a property of light called its wavelength. Wavelength is also related to the frequency of light, which is itself related to the energy of a photon. Another way to think about light is by way of an analogy to sound. Sound waves also come in different frequencies, which we call the pitch of a sound. So colour is to light as pitch is to sound. For instance, I can make sound of a low pitch, la 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 la, or I can make sound of a high pitch, la 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 la, just as I can make low frequency light, like red, or high frequency light, such as blue. When a large tuning fork is struck, a low pitch sound wave is created. The ends of the fork vibrate back and forth slowly at a low frequency. This vibration creates a pitch we hear as it is transmitted through the air. When he strikes a small fork, a high-pitched sound is created as the end of the fork vibrates rapidly. Each of the fork's tines are vibrating periodically, pushing the air molecules back and forth, which results in the creation of sound waves. Sound waves repeat at set intervals, separated by a distance, which is the sound wave's wavelength. Low-pitched sound waves have long wavelengths, while high-pitched sound waves have short wavelengths. Additionally, sound travels at some finite speed, which we call the speed of sound, which is much slower than the speed of light. This is why you will sometimes see the source of a distant sound before you hear the sound itself. One of the most well-known examples of this is thunder that follows the lightning. Here we see Curtis and Ross are sending waves along a spring which travel using the same principles that sound waves do. As the wave in the spring passes by, the coil is compressed and then stretched periodically, resulting in the motion of the wavefront along the length of spring. This type of wave is called a longitudinal wave. This is similar to how air molecules are pushed back and forth by a sound wave. Human hearing is limited to a range of pitches from about 20 Hz to 20,000 Hz, which means that it's possible to create sound waves that have a pitch that is either too high or too low for humans to hear. A sound wave that is too low for us to hear is called infrasonic. And some animals, like elephants, use infrasonic to communicate. Although a human couldn't hear it, it is possible for them to feel infrasound as a vibration. Sound waves that are too high-pitched for us to hear are called ultrasonic, and are also useful for navigation in animals like bats. Just like sound waves, light waves are characterized by their properties of wavelength, frequency, and propagation speed. The speed of sound depends on things like the temperature and density of the air and even the pitch of the sound. This is contrasted by light, which has a fixed speed in a vacuum and very little wavelength dependence travelling through a medium like air. However, light waves travel at incredibly high speeds compared to sound waves. The speed of light is just a whisper shy of 300,000 kilometers per second. The symbol c is used to denote the speed of light, which has a precise value of 299,792,458 meters per second, or 2.9979 times 10 to the 8 meters per second. While sound waves are longitudinal compressions, light waves are actually a type of transverse electrical and magnetic wave. Scientists use the term electromagnetic radiation to describe light. The longest wavelength light that our eyes are capable of detecting are approximately 700 nanometers long, which corresponds to a deep red. The shortest wavelength of light that we can see is approximately 400 nanometers long, a deep violet. Therefore, the range of light between 700 and 400 nanometers is often called visible light. This can be seen as a rainbow of colours, which we see. In order of longest to shortest wavelength, the colours are red, orange, yellow, green, blue, indigo, and violet. Just as there are infrasonic and ultrasonic sounds that human ears can't hear, there are colours that human eyes can't see. The visible spectrum is only a narrow slice of the entire electromagnetic radiation spectrum. In order of longest wavelength to shortest wavelength waves, the bands in the electromagnetic spectrum range from radio waves to infrared light. This is followed by the familiar visible spectrum, then ultraviolet light. As we approach shorter wavelengths, we have X-rays, and the shortest wavelength light, gamma rays. Going from long wavelength electromagnetic light to shorter wavelengths is the same as going from low frequency light to higher frequencies. Even though there are all these types of electromagnetic waves, they all travel at the same speed, the speed of light. We call individual particles of light photons. This is the same as saying that light is quantized. Each photon is a small, discrete packet of energy. The energy of a photon is related to its wavelength and frequency, and therefore its colour. With a beam of light, there are trillions of photons, each with their own energy. The energy that a photon carries is proportional to its frequency and inversely proportional to its wavelength. This means that X-ray photons, which have fast frequencies of oscillation, carry large amounts of energy. As a result, X-ray photons have very short wavelengths and can easily pass through human tissue, with the exception of bones. This allows doctors to take X-ray images of your skeleton. On the opposite end of the energy scale, radio waves have low oscillation frequencies and therefore long wavelengths, because they carry tiny amounts of energy. While exposure to X-rays can cause tissue damage, radio waves transport such small amounts of energies per photon that they are considered safe to use in modern telecommunications. We have talked about light in terms of waves, discussing features like wavelength and speed. We have also talked about light in terms of particles, or photons. So which is it? Are photons waves, or are they particles? Well, the physical theories that describe light tell us that light behaves both as a particle and as a wave. It can take a little bit to get your head around the idea of light being both wave and particle, and it took scientists a long time to work this out, with arguments debating the nature of light and matter in the 1600s through till the early 1900s. This idea is known as wave-particle duality. The duality being that light can act either as a wave or as a particle, depending on the situation you are considering. Now that we have covered the basics of light, let's take a look at how we can measure and use light to gain a greater understanding of black holes and the universe.